Hello everybody. In the previous talk, I had discussed about one of the serious limitations of ground based astronomical observations. So, I will continue from that point to just for continuity, let me try to explain what the main problem is. When light from a distant object passes through the Earth's atmosphere, it gets disturbed in various ways. We will try to understand how that is in the next few slides. This effect is called atmospheric seeing. The cause of seeing is because the atmosphere is not a stable medium, it is turbulent, it is inhomogeneous and it is continuously changing. Now, there are various causes which leads to these disturbances in the atmosphere. On one hand, atmosphere is being heated continuously by solar radiation, and it is not uniformly heated everywhere. There is difference in heating in different parts. There are radiation coming from the ground, there are human activities, there are all kinds of disturbances which, and there are winds blowing. So, similarly, there are many disturbances which cause atmosphere to be inhomogeneous and turbulent. Now, to understand what the effect of this is in light which travels through the atmosphere, we need to understand what the structure of this disturbance is first of all. And this entire subject was studied long ago, initially by Kolmogorov and others, and then has been subsequently worked upon over the last several decades, and we have a pretty detailed understanding of what the atmosphere does, how it impacts light traveling through it, and how to work around it. So, that would be the main topic of this discussion, and in the end I will highlight some efforts which are being made in India to build one of the largest facilities, observational facilities which are upcoming, the 30-meter telescope. So, before getting into that, let us understand what the atmosphere does. Energy is injected into the atmosphere at very large scales, typically by the sun, the earth and so on and so forth, which leads to bulk movements of parts of the atmosphere. But these bulks, these parcels of atmosphere cannot stay as a single parcel for a long time. It is a gas after all, and gas in motion, and gas which is being and a gas which is disturbed also. So, which means that these parcels continue to break down into smaller and smaller parcels as they move, and this process goes on for a while till they are small enough that subsequent breaking up does not happen. So, there is a outer scale at which energy gets injected into the atmosphere, the large scales, and an inner scale at which the parcels of the atmosphere or the eddies or the small blobs of the atmosphere do not further break down into much smaller pieces. And at any point of time, the entire atmosphere will have structures at all these size scales, starting from the largest all the way to the smallest. So, the light is passing through an atmosphere which has movements at parcels sizes of all these size scales. That is a point to keep in mind. Now, what we need to also realize is that as light travels from distant objects which are very far away, most of the time it is passing through practically empty space. The number of particles in space is of the order of 0.1 particle per centimeter cubed, very low density. On the other hand, on Earth, the number of particles per centimeter cubed could be as large as 10 to the 19, which means the atmosphere is a medium which is 10 to the 20 times denser than empty space out there. Empty space still have some particles, but it is so low in density that you can practically consider it empty space, which is not the case with the atmosphere. So, the light has to pass through this very dense atmosphere which compared to what is space. Now, what it does to the light is, in the previous lecture I explained to you how light from the distant source arrives after passing through enormous distances as plane wavefronts. The curvature of these wavefronts are so negligible because the distances are so enormous that you can practically treat them as plane wavefronts, and the rays of light can be considered normal or perpendicular to these wavefronts. Now, when these wavefronts or these light rays pass through the turbulent atmosphere, they get disturbed. What it means that a set of rays which are starting at the same time above the atmosphere, when it passes through the atmosphere, they travel different distances. So, while this wavefront appears to be plane here as a surface, plane surface, the wavefront at the bottom of the atmosphere as the light passes through is no more a plane wavefront. It is a corrugated wavefront or a distorted wavefront, because along each line of sight through the atmosphere, the light would have traveled different effective distances. And this is okay if it was static. The problem is, this is not a static situation, this atmosphere is continuously changing, which means that all the consecutive wavefronts as they pass through the atmosphere will end up having different distorted shapes as they arrive at the telescope. And this distorted shapes is what leads to the severe degradation of the image quality which a telescope can produce at its focal plane. Now, this is very often quantified, the effect of atmosphere is very often quantified by a parameter called Fright parameter. Now, this is usually denoted by R0, it is a function of wavelength, but typical values of R0 is about 10 centimeter. What it means is that you can, I will make this quantitative little later, but you can imagine this to be the approximate size of an atmospheric blob size. The typical atmospheric blob size is of the order of 10 centimeter on the smaller side, which means that at distances which are separated by 10 centimeter or more through the atmosphere, the effective path length the light travels through, the effective distance that light passes through can be completely uncorrelated. So, one ray of light which is passing here, another ray of light passing here which is more than 10 centimeter or so separated, the effective distance they will pass, if they will see at any given time would be completely uncorrelated. They would be no relation with each other. Clearly, if two rays are passing right next to each other through same part of the atmosphere which is smaller than 10 centimeter, they will roughly pass through the same distance, effective distance. So, this kind of indicate the size scales at which atmosphere decorrelates the effective path length of rays passing through it. And what is to be kept in mind is this decorrelation, or the time over which the shape of the wavefront, distorted wavefront change substantially, is of the order of few milliseconds in typical atmospheric conditions. So, every few millisecond the shape of that wavefront which has passed through the atmosphere almost completely changed with no correlation to the shape it had a few milliseconds away. So, which means that if you have to work around this problem, you have to measure the wavefront shape at time scales which are faster than the time scales at which the shape is changing. That puts a big challenge. So, what it effectively does to the image of a star is illustrated here. This distortions introduced by the atmosphere. This is the image of a star taken with a very large telescope. The Betelgeuse is a very bright star. So, which means that you can take a very short exposure which is shorter than this time scales over which the atmosphere changes. So, at each instant of the time you can see that the light has been split up into a large number of tiny or blobs of light, which all stays together, but they are all made, there are a lot of substructure in the image. So, this is the image of a star, a bright star formed by a very large telescope, and a movie is made out of many subsequent images taken several milliseconds apart. So, you can see many things. One is the light is already split up into small parts, and you can also see that big blob of light is actually moving around all over the place. It is not like it is split into small parts and staying at one place, it is also jumping around all over the place. So, this net effect of this is called atmospheric seeing. If I take, instead of these small short exposures, if I take a very large exposure, a very long exposure of this star, during that exposure time you can imagine that this blob of light would have jumped around all over the place, filling with light over a large area. So, effectively what you see as the image of that star at the telescope's focal plane is a big area of light, big area which is filled with light, and this effect is called atmospheric seeing. So, let us try to understand how this works and make it a little bit more quantitative. To understand that, we need to understand what happens when light passes through an aperture, let us say like a circular aperture. You can think of a telescope as a circular aperture which on which beam of light is incident. So, if we imagine the situation where a circular aperture is illuminated by a beam of light from the back side, the light bends as it passes through this aperture. It is called a property of light called diffraction, and what you see on a screen which is far away is a pattern of light which is a central bright spot surrounded by many rings, and this is called an airy disk pattern. And this is very easily the size and the shape etc., can be very easily understood by diffraction theory of light. So, you can imagine a telescope to be a circular aperture illuminated by a beam of light. In this case, when you looked at this beam of light, it is a laser beam, which means it is a coherent beam of light. The wavefront is not distorted, it is a nice plain wavefront which is forming at the passing through the aperture and forming this airy disk pattern. Now, if I have two such objects in the sky which are slightly separated in angular positions, you will see two airy disks. You can see here airy disk, central spot of one of the airy disk, and the dotted line shows the airy disk pattern of one of the spots, and this is a second spot in the sky which is slightly at a different angular location, and it is airy disk pattern. So, if these two spots are well separated, you will see them as two spots. On the other hand, if these two spots are close by, that they merge with each other, you may not be able to see them as a single star. And intermediate condition is a barely resolved condition which is called Rayleigh resolution condition, where there is sufficient dip in between the image, the airy disk patterns of the two spots to discern them as two spots, and on the other hand, if they are too close enough, you only get an unresolved blob of light. So, the airy disk pattern is the ultimate limit of how close objects in the sky can your telescope resolve. Now, if I look at a 10-meter diameter telescope observing at an object at a wavelength of half micron wavelength, the typical size of the airy disk pattern, angular size of the airy disk pattern, which is the distance from the center of the pattern to the first minimum, is given by 1.22 lambda over d. So, where lambda is the observing wavelength and d is the diameter of the telescope. So, if I put these numbers of 10 meter diameter for the telescope and half micron wavelength of observation, the Rayleigh limit is given by 1.22 lambda over d or 0.01 arc seconds. So, theoretically, if you think of a telescope as a circular aperture of 10 meter diameter illuminated by light of wavelength half micron, you should be able to resolve fine details which are as close as 0.01 arc second separated in the sky. So, let us see what atmosphere does to this. Oh, sorry, before that let us try to understand, yes, let us try to see what the atmosphere does to this. In order to understand that, let us look at this relatively simplified situation, where instead of one aperture, you are putting many apertures, one below the other, to form what is called a grating. So, these gratings have many apertures which are separated by certain distances, and the grating is illuminated from one side at a wavelength of light lambda. So, if I put a screen far away, what you would end up seeing on the screen is a illumination pattern which looks like this. This not look like an airy disk pattern, but it is the combined effect of the light diffracting at each of these apertures and forming this illumination pattern on the far screen. Now, you can see that there are multiple structures here. This does not look like the simple airy disk pattern with a central brightness and rings around it. The multiple bright patterns here and multiple structures here. For example, each of these bright rings, which as they move from the center, reduces in its intensity. So, if I plot an overall envelope on top of it, you get a pattern like this. So, you can see that there is multiple structure. Now, let us try to understand where these structures come from. To understand that, you need to understand what are the structures in the grating which you put through which the light was passed through. At the very minimum, you can think of three size scales here. The smallest size scale is the size of your aperture, denoted here by A. The next size scale is the size of a full opening and a block. So, one opening plus one block, denoted here by D, and the third size scale is the entire size of your grating. So, the smallest is one opening, the next size scale is one opening plus one closing, and then the entire grating, at least three size scales denoted by A, D and W. Now, you can show that the structures which we see here are directly connected to these size scales here. For example, the overall envelope which you see here of the pattern which you see on the far screen, the size of that overall envelope, the angular size of that overall envelope is given by lambda over A, where lambda is the wavelength of the light. So, lambda over A. Then you can also see that the separation between successive maxima are given by lambda by D. And also you can see that the width of this maxima, one of them, is given by lambda by W. So, clearly there is an inverse relation between structure sizes here and structures here. The smallest structure here, which is given by size A, leads to the largest structure in the illumination pattern given by this overall envelope and the lambda by A, because A goes into the denominator, that becomes the largest structure here. Similarly, lambda over D, which is the next size scale, gives the intermediate structure scale here, and the largest scale here, which is W, leads to the finest structure here, which is the width of an individual maximum. So, clearly there is an inverse relation between the way you illuminate your aperture and the way you get the illumination pattern at the image plane on a far screen, and it is an inverse relation. The smallest structure leads to the largest structure here and vice versa. So, now let us look at here at the image of what you see here. This is exactly what is going on. I told you earlier that the atmosphere, because of the disturbance caused by various factors like heating, wind, human activity, etc., or mountains, any disturbance in the flow of the atmosphere breaks down into tiny structures of parcels of air, which is moving around independent of each other, and this is continuously getting mixed up. So, if I take any instant the light passing through it and falling out the circular aperture of a telescope and coming into its focal plane, you expect to see structures in the image which are of inverse size scale as that of the atmosphere. Atmosphere is now acting like a grating, but in the previous slide I show a grating which is static, which is fixed, and the structure sizes are also fixed. Now, atmosphere is again like a grating, but it is dynamic, it is changing continuously, and the light is passing through that atmosphere, which means that the image formed by the light of the light through a telescope will also have information or impact of all that structure which is in the atmosphere. So, the smallest features in this blob of light coming from the largest parcels of the atmosphere, and the overall large scale motion here of the object is due to the inverse of the largest features in that smallest features in the atmosphere. So, there is a clear inverse relation between the largest here and the smallest in the atmosphere. So, we can quantify this in a way we did quantify in the previous slide of light illuminating the diffraction pattern caused by a grating. If the Freud parameter, which quantifies the typical size of atmospheric parcels, is much less than the diameter of the telescope, you can see that the angular size of the image is dominated by the diameter of the telescope, because that is the smallest structure in the system. The atmospheric size is larger than the diameter of the telescope, which defines then the image size. Similarly, the time scale over which that image size changes is given by the diameter of the telescope divided by the typical velocity at which these structures are moving across the line of sight of the telescope. So, for a diameter of the telescope smaller than the typical atmospheric eddy size, angular features are driven by the diameter of the telescope, the time scales are driven by the diameter of the telescope, that is the smallest feature. On the other hand, in case 2, if the diameter of the telescope is much larger than the typical atmospheric size scale, now atmosphere is what defines the typical angular size and the time scales over which things change. Here the angular size scales are given by lambda by r 0, and typical time scales, the fastest rate at which the objects change, are given by r 0 divided by the velocity at which these eddies move across the line of sight. So, which means that the atmosphere is now dominating in defining what is the image size scale as well as what is the time scale over which those images are changing rapidly because of the atmospheric turbulence, and it is not defined by the telescope diameter. So, this is a problem, because when you make larger and larger telescopes, I mentioned earlier that r 0 is typically 10 centimeters, 15 centimeters, etc., of that order. So, any telescope which is considerably larger than that size scale is going to lead to image quality which is defined by the atmosphere rather than the diameter of the telescope, and the size scales, time scales over which that changes is defined by again the atmosphere rather than getting a stable image if you just have the telescope, not the atmosphere and not the changing atmosphere in the path. So, let us try to quantify this a little bit more. I said earlier that light passing through a circular aperture, a coherent beam of light passing through a circular aperture forms a airy disk pattern on a far screen. We also saw that for a 10-meter diameter telescope observing at half micron wavelength, the typical size from the center of the disk to the first minimum is of the order of 0.01 arc second. But on the other hand, if this light passed through the atmosphere before reaching this telescope, the typical R0 value could be of the order of 10 centimeters, which means that defines the image size, overall image size, the area over which the light spreads over the telescope focal plane. And if you plug in the numbers, you will see that the image of the light of the star spreads over a size of 0.5 arc seconds. So, while a star should have been, all the light from the star should have been confined to an area of the telescope focal plane corresponding to 0.01 arc second, here is a situation where it is spread out over 50 times that diameter or 50 times that radius. I show a 0.1 arc second diameter circle here. Compared to this, if this is 1/5 of this. So, the light which should have been concentrated on this tiny area here will get spread because of the atmosphere into an area which is 5 times of this diameter. I can't fit that into the screen, it is that large. So, this is a very serious limitation. The atmosphere totally completely limits to a high extent the image quality that can be delivered by a large telescope looking through the atmosphere. Now, let us try to quantify this a little bit more to understand how to work around it. We need to quantify it a little bit more. The way to quantify the atmospheric turbulence is to define what is called a structure function. It is very easy to understand. You take the temperature at a location, which is let us look at this part, temperature at a location, and subtract the mean temperature at that location from that value, instantaneous value. Similarly, go to a distance r away from that location and take the temperature at that location, subtract the mean value of the temperature at that location, and the difference between these two quantities is called the, and average that over the square of that averaged over a large number of regions is called the temperature structure function. So, what you are really trying to measure is how the temperature at a location deviates from the mean value there over a large area and on a statistical sense, and that is what is being quantified by this value. Clearly, as you change r, which is the separation between the two spots at which you measure the temperature, you will get a function. And very often in a particular region of the sky, the mean temperature at two locations over a large area would be approximately same, which means that this deviation reduces to these mean values just cancel out, and this deviation is just the difference between the temperatures at those two locations squared and averaged over many such patches. So, this is clearly a function of r. So, what is understood is that for typical kind of turbulence which we see in the atmosphere, the temperature structure function scales like the separation raised to the power of 2/3 and multiplied by a coefficient which is called the structure constant. So, the structure constant multiplied by r raised to 2/3 is the typical nature of the structure function in standard atmospheric conditions. Now, you can connect this temperature variation to variations of the refractive index at any temperature is given with respect to that at a standard temperature by this expression, and when you plug that expression back in here, you can see that the refractive index structure function scales like the refractive structure constant times r raised to 2/3. So, if you then translate this refractive index into phase of the light passing through the atmosphere, phase is nothing but 2 pi by lambda times the distance travelled in a given path. So, if you can translate that into phase, you can write this expression as 2.91 2 pi by lambda squared r raised to 5 by 3 integral of the Cn squared. You can see that the Cn squared is here. So, the total phase is the integral of the path which passes through which the light passes through in the atmosphere, and that integral everything else other than this Cn squared comes out of the integral, and with the integration it gives you an r raised to 5 by 3 power. So, the phase structure function scales like r raised to 5 by 3, and it has a lambda raised to -2 dependence. Now, if I look at the sky in a given direction at a star which is located in the sky, I can compare, I can denote the angle at which I look at the sky with respect to the direction toward the zenith by this variable z. Then you can show that for certain kind of atmospheric conditions like the plane parallel approximation, certain approximation for atmospheric conditions, you can denote this effective path length through the atmosphere, which is this S, by the path length toward this direction multiplied by tan z. So, sec z, sorry. So, h this distance is given by this by sec z. So, which means that in any direction in the sky you can quantify the effective path length, and which means this integral along that path in terms of the integral towards the vertical direction at that location and the sec z function. And this is valid for angles up to few tens of degrees. When these angles become larger than few tens of degrees, this sec z approximation and the plane parallel approximation may not hold good, and you need a better approximation. But if you plug that back into this formula, you get the phase structure function to be 115 r raised to 5 by 3 lambda squared sec z, and the integral of the refractive index structure constant toward the vertical direction in the sky. So, if I can measure the refractive index structure constant integral along the vertical direction, and if I know what the angle at which I am looking at any part of the sky, I can find out what is the effective phase structure function in towards that direction of the sky. Now, we can show that this phase structure function of this part of the phase structure function can be absorbed into what is called the Freud parameter R0, which I defined earlier. R0 is defined in this context as the radius of the aperture within which the phase structure function is 1 radius squared. So, if we put that condition in, you reduce these parts into constant 6.88 and the remaining part of this expression into R0, and clearly this r raised to 5 by 3 comes about. So, the phase structure function can be expressed in terms of R0, where R0 is defined like this, which is the radius over which the average phase structure function variance is 1 radian squared. So, you can also see here that R0 is a function of wavelength. So, if I want to denote R0 as from this expression, so R0 at a wavelength lambda, it is related to R0 at a wavelength lambda 0 by lambda over lambda 0 raised to 1.2 cos zenith angle raised to 0.6. It is easily derivable from here. So, the Fright parameter is a function of wavelength to a power of 1.2. That is all I have already described here. The RMS phase fluctuation in a circular aperture of radius r0 is 1 radian. That is the definition by which you derive this expression. Now, similarly to r0, you can also define what is called the theta 0, which is the angular separation in the sky within which the RMS fluctuation is 1 radian, and that is nothing but this r0 divided by the typical height of the atmospheric layer where the turbulence is dominant. So, you just apply that value here and you can get this one part of the h into this equation, and it gets and the integral comes out and you get theta 0 which is nothing but r0 times r0 by h in this way. And similarly, you can calculate what is the time scale over which atmosphere changes, which is given by the velocity at which a blob of size r0 passes across your line of sight, and you plug that back into this equation, you can get the time scales over which atmosphere size scales changes. So, r0 denotes the typical atmospheric patch size over which you can consider that the RMS phase fluctuation is small, of the order of 1 radian. Theta 0 is the corresponding angular separation in the sky, which depends on the height at the atmosphere in which most of this turbulence, or the effective height in the atmosphere where this turbulence happens, and tau 0 is the time over which the structure function or the shape of the wavefront changes, and that is given by the velocity at which these r0 size blobs move across your line of sight. So, these parameters are very often, these models of the atmosphere are very often determined through measurements empirically, and then fitted using various atmospheric function profile models. A very popular model is what is called the HP model, given by this. If you look at the previous expression, it is this Cn squared h which is the only unknown here, which needs to be quantified for a site, and once that is quantified, you can calculate all these parameters r0, theta 0 and tau 0. So, experiments are done at sites where you want to set up astronomical observatories to determine the Cn squared profile as a function of height by various methods, and then models are fit to that profile. And this HP model is one typical model which is very popularly used, where it is parameterized by the height at which most of the turbulence is can be said to be effective height of the turbulence. Cn squared is been already defined as the structure constant of the refractive index, and W and A are parameters which are adjustable for local conditions, and that is determined through actual measurement. For example, an HP 5/7 model gives r0 to be 5 centimeter, theta 0 to be 7 microradians, and in a typical 5/7 model, A is 1.7 10 to the minus 14, and the velocity of wind is 21 meter per second. So, under those conditions, we plug that into these numbers into this, you end up getting r0 and theta 0 of this order. So, that is how atmosphere properties are characterized. Now, that we understand how that is characterized, we need to understand how we can correct for this atmospheric effect. Now, that is done by what is called an adaptive optic system. So, let us try to understand how an adaptive optic system works in this slide. You are trying to study the fine structure details of a galaxy, which is denoted by this thing here, which is your scientific target. Now, the light from that target passes through the atmosphere. Above the atmosphere is plane parallel. As it passes through the atmosphere, it gets distorted because of the turbulence and finally falls on your telescope. So, this rectangular block denotes your primary mirror of the telescope, and it passes to the focal plane of the telescope. Now, in order to correct for this atmospheric turbulence, you need a reference object in the sky, which is very often a reference star, a point source in the sky, which is very close to your science target. So, that the light from both the reference target as well as your science target passes through the same part of the atmosphere. So, you want a source which is bright enough, a star which is bright enough, which is close by to your target, which can be used as a reference object. So, the light from both of these pass through the same atmospheric layers, get distorted the same way and fall on the telescope's primary aperture. And then at the focal plane at the back of the telescope, let us forget this surface for this moment, I will come to that in a minute. It reflects off this surface and reaches what is called a beam splitter. What the beam splitter does is, it splits the light coming from the science target in this direction and the light coming from your reference object in this direction. So, the light from the reference star is what comes here, that is what this beam splitter does. And here there is something called a wavefront sensor. What it does is, it measures the shape of the wavefront falling on this sensor as they come from, as originated from the reference star. So, if the atmosphere was not there, you would have expected a plain wavefront here, but because the wavefront is distorted as it passes through the atmosphere, you get a distortions measured by the wavefront sensor. Then wavefront sensor instantaneously from the measured distortions recalculates the shape of the wavefront through a computational process and provides that information to a deformable mirror. The shape of the deformable mirror is instantaneously corrected to exactly compensate for the distorted wavefront which is arriving here. So, that what reflects off becomes a plane wavefront. So, let me repeat this again. Using the light coming from the reference star, which is sent by the beam splitter toward the wavefront sensor, you measure the instantaneous distortions introduced by the atmosphere, reconstruct the shape of the wavefront and change the shape of this deformable mirror exactly in a way so as to get plane parallel wavefronts here. So, you compensate exactly the effect which is introduced by the atmosphere. So, to understand how this works, let us try to see how first the wavefront sensor works. Now, a simple minded wavefront sensor is just made of an array of lenses. So, you think of these as several lenses arranged in a two dimensional array, some set of lenses here. So, if the wavefront which is falling on these lenses is a plane wavefront, each of these small lenslet will form an image at its focal plane. So, from each lenslet you get a spot on the focal plane. However, if the wavefront which is arriving here is distorted like this, the light which is falling on this lens will be tilted, which means that the spot which is formed by that lens would move to a location compared to where it should have been if the wavefront was plane. So, at any part of the wavefront over an area corresponding to the lens size, you can measure the local slope, how much this is tilted with respect to a plane wavefront which is untilted at this as that part falls on this lens, and that leads to a movement of this spot as formed on the image plane. So, by measuring the movement of these spots with respect to its grid pattern which would have got without a distorted wavefront, you can know what is the instantaneous slopes of this wavefront at each of these parts. Now, by stitching together the instantaneous slopes, you can measure the overall shape of this wavefront. and that is what this wavefront sensor does. Now, once that information is obtained, you have to use that information to change the shape of the deformable mirror, and the way it is done is the following. You have this wavefront which is distorted falling on the deformable mirror. The shape of the wavefront, the deformable mirror is changed exactly in a way that as this wavefront falls on the deformed mirror and reflects, it becomes plane parallel wavefront. It is just the shape exactly compensates for this distortion, and the reflected wavefront becomes plane parallel, and that is what this deformable mirror does. So, what you get here is corrected wavefront which passes through the beam, the light which is coming from the science target passes through the beam splitter and forms a fine diffraction limited image on your science camera, which is completely compensated for the atmospheric effect. So, that is how an AO system works.